looking at 3 populations and not 2 means that we have to use a different statistic. We have to use analysis of variance. ANOVA, or analysis of variance, is used to determine if 3 or more populations are different or distinct. It's a generalization of the 2-population t-test. Formally, ANOVA provides a statistical test of whether or not the mean of several groups are all equal. Using, instead of a p-value, it's called an F measure. And in ANOVA, you can have 1-way, 2-way, 3-way, n-way ANOVAs. The most common ANOVA is just simply saying, is 1-way, is there any of the 3 populations different? Doesn't distinguish which pair is different. So ANOVA tests can be used just like the t-test if you have 3 or more clusters. So here's some data, and we can see with our eyes, it looks like there are 3 distinct clusters. ANOVA could be used to determine if those 3 clusters are statistically different or whether it's just an illusion of your eyes. ANOVA can also be applied to n populations, not just 3 or 4. We could have 100. We could have 100 populations or 100 comparisons. We could decide whether these overlap or don't overlap and how much they do. So when we start doing multiple pairwise comparisons, we can run into certain problems. And this is what we typically have to deal with in metabolomics and genomics and proteomics. Because we can often measure 100 or 500 or 1,000 different metabolites or concentrations, and if we're measuring those for the cases and we're measuring the same ones for controls, then potentially we could have 100 or 1,000 different pairwise t-tests. So if we've got 100 different t-tests, and if we use a standard alpha threshold of 0.05, what are the odds that one of these t-tests is actually going to be false? So we can calculate that, and we can run the numbers, 1 minus 0.05, 95, 0.95, so 100 different tests, subtract from 1. We'll come out with a 99.4% probability that one of these t-tests is going to be false if we ran 100 t-tests. So if we want to be certain that none of these t-tests is going to be false, we can use and adjust our threshold from 0.05 to 0.0005, simply dividing that by the total number of tests. So this is called the Bonferroni correction, and it allows you to avoid or having a threshold that avoids having a false positive. Now, what people found that the Bonferroni correction was actually far too strict, and that almost everything that people measured could not meet the Bonferroni adjustment. So that even to our eyes and our intuition said these things really are different. When applied to the Bonferroni correction, it kept on coming up as saying, no, it's not significant. As a result, people started to reanalyze the rationale behind the Bonferroni correction. And 2 statisticians, Benjamini and Hochberg, came up with perhaps a better, softer approach. They noticed that if you did 120 different t-tests and found 20 that had a p-value of less than 0.5, what are the odds that one of these is going to be false? And they determined that probability would be pretty much close to 1. So to correct that, what you would do is then adjust the p-value by dividing by approximately 20. So instead of having 0.0005, you would have 0.0025. So this is a softer adjustment. It's not as strict as the Bonferroni. And this modification to the Bonferroni correction, called the Benjamini-Hochberg correction, is what's now standardly used. This is not called a p-value, it's called a q-value. So the Benjamini-Hochberg values allow you to calculate t-test values, but to correct for the false discovery rate. And so when you're comparing cases versus controls with univariate data, say for metabolomics, you should look at the q-value and to see which ones are significant based on their Q value, not their P value. We're going to switch gears here and we're going to talk about data comparisons and data dependencies. So this refers to situations where we're typically looking at the effects of some intervention or a before and after study, where we're comparing one variable before to another variable after to see what's happening. Sometimes in other types of experiments, we'll be doing a measurement on observed property, and then we'll compare it to the predicted property. So we plot observed versus predicted. So it can be before and after, observed versus predicted. In these types of studies, we're essentially measuring multiple samples, measuring multiple subjects, and we're trying to determine whether our predictions match with the observation, whether the before and after treatments are having an effect. The way that we typically analyze these types of data sets is through something called a scatter plot. This is a scatter plot showing comparison between a husband's age and a wife's age. And what you can see is that generally a husband's age matches the wife's age. People marry and generally grow old together. There may be situations where you can find one spouse being much older or much younger than the other. But as seen in this plot, it's relatively rare. So we can infer from this information that generally people of the same age tend to marry the people of others of the same age. This is called a scatter plot, and scatter plots are widely used in many fields of statistics. Scatter plots help you identify a dependency between two variables. It allows you to determine before and after effects, predicted versus observed. The pattern that you see, or the relationship that's detected, is often described as a correlation. So we can have positive correlations that we saw between husband's age and wife's age. We can have things that are totally uncorrelated. It might be hair color, if we had something where grades of hair color, or it could be probably weight would also be relatively uncorrelated between husband and wife. We can also have negative correlations. So instead of a slope that's positive, we can have a slope that's negative. An example of an anti-correlated function might be strength and age. And certainly as people get older, they get weaker. And so we would see a negative correlation. Now, the quality of correlation is something that is also important. Here are some examples. We can have high correlations, we can have low correlations, and we can have perfect correlations. The correlation between husband's age and wife's age is highly correlated. Probably the correlation between husband's weight and wife's weight is probably poorly correlated. Perfect correlations are things that we almost never see, but they do occur in certain physical phenomena. With correlation, we actually calculate a number, and it's called the correlation coefficient. And the equation for calculating correlation coefficient is given in above. And with that, we can come up with not just simply qualitative assessments of good, poor, non-existent. We can actually come up with a number. A perfect correlation has a correlation coefficient of 1. A pretty good correlation has a coefficient of 0.85. A poor correlation has a coefficient of about 0.4. The correlation coefficient is something called the Pearson product moment correlation coefficient, or the coefficient of linear correlation. It's a quantitative measure to assess how good a model is, how good a prediction is, how closely related two variables are, how connected before and after things are. So correlations are an excellent way of assessing predictions, simulations, and dependencies. Now, there tends to be a misuse or abuse of correlations. R is the correlation coefficient. R squared is called the coefficient of determination. They're technically different. You shouldn't confuse them. You shouldn't call R squared a correlation coefficient. It's fundamentally wrong. And generally, you should avoid using R squared when you talk about comparisons. You should just use the correlation coefficient. Unfortunately, Microsoft Word in the Excel software uses the correlation coefficient of determination, and that's what people tend to present. It's unfortunate, and it's leading to a misuse and abuse of the correlation coefficient. You can also evaluate whether correlations are significant or non-significant. Just like with normal distributions, getting 30 or 40 samples is often sufficient or necessary to determine if the correlation is robust. If you just have 3 examples, probably it's hard to determine if it's significant. So on the left, we've got a coefficient of 0.85 measured for about 150 different data points. Under most statistical tests, that would be significant. On the right is an example where we have a correlation coefficient of 0.99, almost perfect, but it's for 3 points. Is that really significant? Well, what could happen is that you measure 2 more points, and suddenly the correlation went from 0.99 is now 0.05. So this is sort of saying that this correlation is not significant, but it would have been impossible to know unless you were able to measure the 2 extra points. So the intent is to have statistical methods that could look at just the 3 data points and determine whether it's likely significant. There are other tricks that people have determined or used and abused to improve quality of correlations and correlation coefficients. One trick is to collect a lot of data at one extreme end and then another set of data at another extreme. And so the result is that you have 2 clusters, one at one corner, another at another corner. And so you can get a great correlation coefficient. But the question is, what's missing in the middle? Does it really spoil the overall correlation? Another trick that people have used, and we just showed you examples, is just to use a small number of data points and then argue that the coefficient is high and therefore the correlation is significant.